Okay, so we learned how to take a formula and turn it into a percent. Today we're going to learn how to turn a percent into a formula. Make sense? Going backwards. So when calculating it, we're going to get the ratio from the percent composition. We're going to get the ratio of atoms, so we know what the subscripts are, from percent composition. So somebody does a lab, tears a chemical into pieces, weighs what the pieces are, tells you what percent of every element you have. So you're going to take that percent data, and you want to turn it into moles. But we cannot turn percents into moles. What can we turn into moles? Can we turn percents? Can we turn into moles? No. We can turn liters into moles, grams into moles, or particles into moles. Those are the three things we do with moles. So I need one of those three. So percent composition, the easy one of those to get is the grams. Because percent composition doesn't matter how much you have. So you can pick any amount. It doesn't matter which one you pick, but there's one that if you pick it, it makes the life really easy. Pick 100 grams. Picking 100 grams makes it easy to turn percent into grams. Because if something is 25% copper, and you've got 100 grams of it, how many grams of copper do you have? 25. See the joy of picking 100? We could pick any number, but we would have taken that number and multiply it by the percent. Right? We could have picked 4 grams, but then we would have had to take 25% of 4 and figured out it was 2 grams. I don't want to do all that math, or it was 1 gram. I don't want to do all that math. I'd rather just take percents turn into grams because I assume I have 100 grams. Right? Then grams I can turn into moles. So I do that for every percentage I have. It'll tell me the moles of each piece. And that's what I need to figure out the subscripts, because the subscripts are mole ratios. So I just have to take the moles I got and turn them into mole ratios. That means put the moles over each other. Find the lowest whole number ratio by dividing all the other ones by whatever the smallest one is. Whatever the smallest number of moles you have. And it's going to be a whole number ratio. Now, it doesn't say it's going to be a whole number. It says it's going to be a whole number ratio. Sometimes it will be a whole number. You'll get something like 3.99. 3.99 is pretty close to 4. 3.99 is close to 4. So that would be like 4 to 1. But what if you got something like 2.5? That doesn't sound like a whole number ratio, does it? But it is. Okay? If you write it the way your math teacher doesn't want you to write it. Because 2.5 is 2.5. 2.5 is 5 halves. That's a whole number ratio, 5 over 2. Does that make sense? So some simple fractions may need to turn into whole numbers, things like quarters, thirds, halves. Right? All right, so let's do an example. This is the kind of data you're going to get. Got a compound made of 38.67% carbon, 16.22% hydrogen, and 45.11% nitrogen. What is its empirical formula? So what we're looking for, it says, what is the empirical formula? We know it's C, H, and N. And we're looking for the little numbers that go down here. And those numbers are going to be true in atoms, so they're going to be true in moles. In water, it's 2 hydrogen atoms to 1 oxygen atom. In water, it's 2 moles of hydrogen to 1 mole of oxygen.
Do you just write it in the order that they give you?
There is an official order. For right now, just do it in the order they give you, unless you've got a metal, non-metal.
Okay.
That makes sense? If you got a metal, you're going to have to put the metal first. Okay. So we assume 100 grams, so I can say that I've got 38.67 grams of copper. Okay. Are we okay with that? So I take, because if I got 100 grams of 100 grams, 38.67% of 100 is 38.67. That's why you pick 100, because it makes the math easy. And then take those grams and turn them into moles. Oh, I'm trying to get someplace. You're in the wrong place. So, Dusty. After you leave here. Okay. So, that's 3.22 moles of carbon. That's not a whole number. It's not supposed to be. Same thing with hydrogen. 16.22 grams of hydrogen. Because there was 16.22% hydrogen. Take grams of hydrogen, turn into moles of hydrogen. $16.1, not a whole number. And then I do the 45.11 grams of nitrogen, because it was 45.11% nitrogen. So those percents just become grams because we assumed 100 grams. And there's my moles. Now I need to see the ratio of those moles, because the ratio of those moles should be whole number ratios. So it says pick the smallest number here. What's the smallest number here? 3.220. Doesn't matter whether I pick moles of carbon or moles of nitrogen. But the key is the smallest number is 3.22. So now I'm going to divide everything by 3.22 moles. I picked the nitrogen. Didn't matter which one I picked, I'd have gotten the same answer. Okay. The obvious one, 3.22 moles of carbon for 3.22 moles of nitrogen. That means I got 1 mole of carbon for 1 mole of nitrogen. So in my formula, every time I have a carbon, I got to have a nitrogen. Because that's how you get equal amounts inside of it. Make sense? And then I got to do the other one. The 16.1 moles divided by 3.220 moles works out to be 5. 16.1 divided by 3.220 is exactly 5. Could have come out to be 4.99 and we still would have called it 5 because it's supposed to be a whole number ratio. So that's all we need to do except for writing numbers.
So how come instead of put the carbon and the nitrogen to 50% even though they have the same?
Because nitrogen atoms are heavier than carbon atoms. So it's going to be a bigger mass percent. And you see it's by the fact that this, 12 to 14. It's actually that ratio is the difference in the percentages. Yeah. So what numbers do we write? Well, what's the number next to carbon?
5 or 1.
1. What's the number next to hydrogen? 5. And what's the number next to nitrogen? 1. That's the formula. If you took this and found the percentages along the way, it would match up with the percentages you started with. That it would be 38 points. This would be 38.67% carbon. Okay? So horrible. It's a little bit tedious, but we get to skip some math because we get to do in our heads percents to grams. Okay? Because if you didn't pick 100, if you picked 15 grams, you'd have to take that 15 grams and multiply it by 0.3867. And then you take those grams and change it to moles. It would still work, but you'd have to do some more math. And you'd round more times, which would make that last digit vary a few times. So let's try one of my favorite chemicals. Caffeine. Liquid sleep. No. Caffeine is 49.48% carbon, 5.11% hydrogen, 28.87% nitrogen, and 16.49% oxygen. What is its empirical formula? So where do we start this problem? Turn percentages into grams. So let's give this a try. If I have 48 point, if I assume 100 grams, then I can say I'd have 49.48 grams of carbon, 5.15 grams of hydrogen, 28.87 grams of nitrogen, and 16.49 grams of oxygen. So I take the percents, turn them into grams, because I assumed 100 grams. Then I take the grams and change them into moles. 1 mole for carbon is 12.01 grams. Some of you may have accidentally memorized that by now. And that is 4.120 moles. For grams of hydrogen to moles of hydrogen, 1 mole is 1.01 grams. So 5.15 divided by 1.01 is 5.10 moles of H. Same for nitrogen, grams of nitrogen to moles of nitrogen. 1 mole is 14.01 grams. 28.87 divided by 14.01 equals 2.061 moles of N. And for oxygen, see, it's getting tedious, not hard. Grams to oxygen to moles of oxygen. 1 mole is 16.00 grams. So 16.49 divided by 16 is 1.031. Everybody okay with that? Simple math, change grams into moles. Now we want mole ratios. Which of those moles is the smallest? Moles of oxygen. So I'm going to divide the other 3 by moles of oxygen. So if I take 4.120 moles of carbon and divide it by 1.031 moles of oxygen, I get and I get 4.07. Oh, no, that's wrong. I was missing a 1. 3.996. So if it was 3.996, last few, where are we at? So if it was 3.996 moles of carbon for every mole of oxygen, that means it's 4 carbons for every 1 oxygen. Look at that. Okay, I take the 1.031 moles of oxygen, and it was what, 5.10 moles of hydrogen? That's 4.95. As a whole number ratio, whole number ratio is going to get you pretty close to 4.95? 5. Because I'm not going to do fractions at the 20th. Because that's what we'd have to do if we wanted to do 9.5, right? 19/20ths? We're not going to do 19/20ths. So that's 5 hydrogen for every 1 oxygen. And then, man, it keeps doing that like that. Then we had 2.061 moles of nitrogen for 1.031 moles of oxygen. Do you actually need to do the division on this one, or can you see what the answer is going to be? It's 2 to 1. Right? So I've got carbon, hydrogen, nitrogen, oxygen. We decided the oxygen was 1. And that made the carbon 4, because we had 4 to 1. Made the hydrogen 5, and nitrogen 2. Pretty straightforward. Find the moles, do the division, divide by the smallest. Oh, well, that's it. That's the one I want, actually. So, determine the empirical formula of a compound that's 52.9% aluminum and 47.1% oxygen. Oops, 52.9%. Aluminum, 47.1% oxygen. I'm going to assume 100 grams so that I can write 52.9 grams of aluminum and 47.1 grams of oxygen. Change the grams of aluminum into moles of aluminum. Grams of aluminum to moles of aluminum. 1 mole is 26.98 grams off the periodic table. 2.9 divided by 26.98 gets me 1.96 moles of aluminum. 47.1 grams of oxygen. Change grams of oxygen to moles of oxygen. 1 mole is 16.00. And that's 2.94 moles oxygen. Do the division. Which one's the smallest one? Moles of aluminum is smaller, so I'm going to put. Now, it actually works the other way. You just won't recognize the fractions. That's why you want to put the small one, so that you can find improper fractions. Those are easier to find than having a big denominator. That make sense? Small denominators are easier to find than big denominators. The moles of oxygen, and that's 2.94 divided by 1.96. And I get 1.5. So is it 1 or is it 2? Neither. It's supposed to be a whole number ratio. What would this be as an improper fraction? 3/2. It's because it's 1.5, which is 1.5, which is 3 halves, right? So that's 3 O's for 2 ALs. So that means the formula is going to be Al2O3. But of course it's going to be. You didn't have to do all this math. I told you to get to put together aluminum and oxygen. Aluminum always makes the 3+ charge. Oxygen always makes the 2- charge. You do the crisscross, you get Al2O3. Ionic compounds, what we write is always their empirical formula. Does that make sense? Okay. I just want to show you it works and what to do with fractions. Now, what about other fractions? What if you saw 1.32? How would you turn that into an improper fraction? What does it look like? Well, to me, it looks like it's really close to 1 1/3, right? 0.33 for a third, 0.67 for 2/3. So 1 1/3 is 4/3. Does that make sense? What if it was 2.75? Or 2.74 or 2.77? That's 2 3/4, right? Which is, that's 8/4, and 3 more quarters is 11/4. Make sense? You've got to take that decimal. So expect you to know quarters, halves, thirds. That's about it. Now we're not going to do eighths. We're not going to do, okay. But pretty awful technique? Nah, just tedious. So, what's this? Why, that looks like number 1, 2, and 3 on page 231. I know we've learned how to do it. It's just a matter of you getting used to doing it.